Hey everyone. So today I'll be going to present a design for a decentralized exchange on which I worked on last year and then I presented it in a crypto exchange conference in this year's summer. So it's about Deeper, which is a design to enhance liquidity in concentrated liquidity AMM, and we use sharing of liquidity to achieve this. So before we proceed in this exploration of design, the question is, what exactly are we trying to achieve? So let's see the motivation behind this. So we know that blockchain has introduced a new kind of economy which is called tokenized economy. So the main element of this economy is tokens, which serve multiple functionalities. For instance, tokens are used to incentivize desired behaviors. For instance, in proof of stake, you get tokens if you do the right thing, and you get slashed if you don't do the prescribed right thing. Similarly, tokens are used as gateways to communities, DAOs, etc. Tokens also represent stake in fan club, for instance, in football fan clubs. And tokens can also be used as derivatives, for instance, contracts representing options. Now that we have this tokenized economy, in order to have a functional tokenized economy, we want that the prices of the token should have these two features. The first feature is that the price of the token should be fair, which means that it represents the actual demand and supply. And second of all, the prices of the tokens should be manipulation resistant, which means that there is a high cost to manipulation. Now, the question is how to achieve these two features. And it turns out that ideally, these two features can be solved if the liquidity for the trading pair of such a token is very high on any exchange. Now, on decentralized exchange, liquidity is provided by agents known as liquidity providers. Now, if we try to understand the incentive of liquidity providers, here is the deal. Liquidity providers are exposed to risk, which is known as impermanent loss. At the same time, liquidity providers earn fee, which is proportional to trading volume. So essentially, it is a fraction of the total trading volume. Since liquidity providers have the same loss, which is a function of the prices, they are incentivized to participate in trading pairs with higher volume. Now, the problem is that what about tokens with low trading volumes? For instance, here we present trading volume for a token, which is a fan token for Sao Paulo Football Club. Now we can see here that the average trading volume for this token is always less than $60,000 per day. If we assume that the LP fee is around 10 basis point, which is 0.1%, then the LP revenue per day will be less than $60. Now, this revenue is pretty small compared to the risks that the LPs are taking. So, how to provide deep liquidity for such tokens which have low trading volume, but they have significant functionality that they're providing? Now, the answer to this question is to use what we are proposing. But in order to understand the design that we are proposing, we need to go through some background prerequisites. So let's start with constant product automated market makers. So in constant product market makers, there is a trading pair consisting of token A and token B. And there is an invariant, which is that the reserves of A times the reserves of P is always equal to L square, no matter what the price P is. Now, L is a constant and it is known as liquidity of this trading pair. So suppose you want to make a swap on this CPAMM, then if a trader wants to buy token A in exchange of token B, he deposits delta RB of token B and in return he gets delta RA. So therefore, the reserves of A reduces by delta RA and the reserves of B increases by delta RB such that the product of both of these token reserves is the same as before, which is L square. So here is the pictorial representation of the reserves. So earlier A reserves were RA and B were RB, and after the swap the reserves of A reduced by delta RA and the reserves of P increased by delta RB. Now we'll try to understand what is concentrated liquidity AMM using the same example that we have been discussing before. So in the previous example, we saw that when the price was P naught, the reserves of A were RA, and similarly for B, it was RB. But when the trader bought a lot of RA in exchange of token B, RB increased by delta RB and RA reduced by delta RA, and the price increased from P naught to P1. Now we can see that in the price range P naught to P1, all the reserves that are shown in dash are not actually used. So therefore, we do not actually need these shaded reserves because these are just sitting idle. All we need is that A should have enough reserves, which is delta RA when the price is P naught, and B should have delta RB reserves when the price is P1. And in between, we don't need these shaded reserves. So therefore, this is what happens in concentrated liquidity AMM, where we assume that these shaded reserves are there, but in reality, they do not exist. And that is why they are known as virtual reserves. And the reserves which are not shaded are known as real reserves. So the mathematical expression of real reserves for A, which is RA prime, is the amount of reserves at price P minus the amount of reserves at price P1. Similarly, for B, it is amount of reserves at price P minus amount of reserves at price P naught. And this is the final expression. And similarly, L, which is the constant, which was the constant earlier, is now known as virtual liquidity of the trading pair in a price interval. Now we can observe that at the edges of interval, we only need one of the tokens. For instance, when the price is P1, then RA prime is 0, while RB prime is non-zero. So therefore, at P1, only B exists. Similarly, at price P naught, only token A exists. And that's what we saw earlier, that at price P naught, we only need token A, and then the trader can buy this token A in exchange of token B. And when the price P1 is achieved, token A reserves, the real reserves become 0, while token B real reserves are non-zero. So here is an illustration of liquidity profile in an example where we have the trading pair ETH/USDC. So on the left, we have a liquidity profile in different price intervals, that is different values of L in different price intervals. And on the right side, we have the corresponding real reserves in different price intervals. Now, the price interval marked with bold is the active price interval, and this interval consists of both Ethereum and USDC reserves. And for the price intervals which are higher than the current interval, it only consists of Ethereum reserves, while the price interval which are below the current interval, it only consists of the USDC reserves. So you can see that if someone wants to buy a lot of Ethereum, then the higher prices only need to have Ethereum because the trader will deposit USDC in return for Ethereum. And if the trader wants to sell a lot of Ethereum, then the lower prices only need to have dollars because the trader will deposit Ethereum and in exchange he'll take USDC. So it makes sense. So now that we are familiar with the required prerequisite, we'll try to understand the design of the deeper decentralized exchange. So deeper works as follows. So suppose there are multiple trading pairs with a same common currency. So for example, we have 5 trading pairs where each token is trading against Ethereum. Now, what Deeper does is that it shares the liquidity for the common currency. And we'll see what does that mean next. So the key idea of Deeper is the following. So instead of allocating the common currency liquidity for each trading pair beforehand in the inactive ticks, which are below the current interval, as we saw before, like USDC was allocated below the active tick, what Deeper does is that it creates one common pool of this common currency, and it allocates the common currency to each token pair when its price reduces and when uh, the price interval becomes active. So, as a result, this increases the real time liquidity as each trading pair has now access to larger reserves of this common currency. So here is a very high level of illustration that earlier the common currency's liquidity was fragmented for each pool. So the amount of liquidity that was accessible by each pool was very less. But now, after having a common pool for the common currency, each trading pair theoretically has a large amount of access to these reserves. And here is a little low level of overview. So in this example, we have two trading pairs with the common currency C represented in red. So earlier, what we were doing without deeper, we were allocating the common currency reserves in the inactive uh, price ticks of both of these tokens. And a lot of these reserves were just sitting idle. And now what we are doing is that we put the common currencies in just one shared currency pool. And uh, this pool then allocates the common currency to the active price interval of both of these trading pairs. And since this pool consists of the common currency from each of the individual pools, this pool is two times larger than just having the common currency in the individual pool. Now, Deeper allows liquidity providers to provision both shared and individual liquidity. Individual liquidity is the traditional form of liquidity provision with no shared access, while shared liquidity is what we'll discuss next. So, in order to understand shared liquidity provision, we define skeleton liquidity. So, skeleton liquidity is the relative amount of liquidity in the inactive price ticks. When LPs deposit the common currency, they need to provide the skeleton liquidity for each of these token pairs. So essentially, they are telling in what fractions the algorithm shall provide the liquidity reserves in the ticks. And this ratio will be calculated with skeleton liquidity, as we'll see in the next slide. So here is the pictorial form of the algorithm. So suppose that we have a lot of trading pairs which are batched using deeper algorithm, and RA represents the amount of shared currency in the common pool. Now, let us say there is a token pair TI slash common currency, and its active price interval, the index of that interval is KI. And suppose that the price of this token pair reduces such that the the previous price interval ki minus 1 is activated, then the following happens. The algorithm secures this amount of common currency and it deposits this amount in the price interval ki minus 1 as real reserves for the common currency. So let's try to understand what is this amount of reserves that are taken from the common currency pool and allocated to the newly activated price interval. So this amount is a fraction of total available shared currency. And this fraction is actually the ratio of uh, the skeleton reserves of tick ki minus 1 divided by the sum of the skeleton reserves of all the ticks starting from 0 to ki minus 1. So we can see that this fraction is always less than or equal to 1. So this means that as the price keeps on reducing, there is always sufficient reserves for the algorithm in the shared pool to be allocated in the current price interval. And when the price goes all the way down to 0, then all of these shared currency reserves are allocated to the last price tick. Now, at the same time, Deeper's algorithm is also reversible, which means that when the price of a tick increases, then the exact deallocation happens, which means that the amount of common currencies that were allocated earlier when the price had reduced, the same amount of common currencies are deallocated from the newly inactive price tick to the common reserves. So this makes the deeper algorithm reversible, and this reversible nature of deeper makes the loss of liquidity providers again impermanent. So now that we know the problem of low liquidity in low trading volume tokens and the background of AMM and the proposed model for liquidity provision, let's try to see what are the benefits of having deeper compared to conventional passive liquidity provision. So this presents the benefits of using deeper in batches of different sizes. Now, since deeper takes the common currency and creates a shared pool out of it, and then allocates that common currency to the active tick, essentially where it is needed, this increases the real time liquidity. And as it turns out, or as you can imagine, the higher the number of trading pairs in a batch, the bigger is the shared liquidity pool, and the higher are the benefits of real time liquidity. So here are the results when the batch size is 3. So this figure represents average liquidity boost on the y-axis. In the x-axis, it represents the fraction of Ethereum that was made available to the shared liquidity experiment compared to the individual liquidity experiment with no deeper. And y-axis represents the amount of boost in shared liquidity experiment compared to the individual liquidity experiment. And this experiment was conducted on historical price data of these three tokens that were traded against Ethereum. So we can see that when the batch size is 3, the liquidity boost goes from 1.6 to 2.2x when the same amount of Ethereum is provided to both individual and share liquidity. Now, if we want to have the same amount of real time liquidity, then the amount of Ethereum that is required in the share liquidity provision reduces by 55 to 61%. Essentially, we need half the amount of Ethereum to observe the same amount of real-time liquidity as it is in the conventional models. Now, if we increase the batch size to 5 assets, then the liquidity increase or the liquidity boost becomes between 2.2 to 3.3x, different for different trading pairs in the batch. While at the same time, the amount of Ethereum required to observe the same liquidity reduces by between 70 to 78%. And lastly, when we have an even larger batch size of 8 assets, then the liquidity boost is anywhere between 2.6 to 5.9x, and the amount of Ethereum for same liquidity reduces from 75 to 83%. So, in conclusion, Deeper is an AMM with an algorithmic pool rebalancing capabilities because it takes the common currency in a shared pool and then algorithmically allocates the common currency in the active tick. Now, liquidity is prioritized to the active tick and not in the passive tick or the inactive tick. So, as a result, this increases the real time liquidity compared to the compared to individual liquidity provision with the same requiring the same amount of the common currency. So this means that now we can have deep liquidity for token pairs with even low trading volume because with the same amount of Ethereum, which is the expensive token in liquidity provision, we can increase the real time liquidity of all the low trading volume tokens in the batch. And as a result, with no additional cost on acquiring capital, liquidity providers can now provide a higher real time liquidity for even low trading volume tokens. So that was what uh, I did last year and then presented this year. And there's a lot of more interesting stuff that is coming next, and I'll keep it posted. Thank you.